This program was brought to you by Koller Institute of Venture at Tel Aviv University.
The topic is really about the activity that we have at the university within the framework of the Center for Nanoscience and Nanotechnology, which was established actually 15 years ago, so long before I had any significant contribution. So I definitely didn't build the center. I started my tenure as the head of the center just a little bit over 4 years ago. And a lot of the insights and what we're trying to do has been motivated by a lot of discussions with Dan Wilensky, which I think many of you know. He's really been, I think, a true inspiration. Practically, we've gained a lot of help and support from Shlomo Oren and Eran Fine, who are two entrepreneur in residence. I'll try to explain later. And Yuval Kupitz, who is working with us at the center, trying to promote many of these ideas. So Nathan asked each one of the speakers to talk about their own story. So I have several stories, and I will not talk about all three of them. So as many academics, I wear several hats. My first hat is as a researcher, and as a researcher I do basic research and some applied research in neuroengineering. I have another hat, which is a VP with the startup company that was established a little bit over 5 years ago. I was the second employee, and it's called Nano Retina, and it's developing an artificial retina. The company is doing very well, still very, very long path to commercialization, but this has been my MBA school, if you want. And the story that I will share with you is the story of running the Tel Aviv University Center for Nanoscience and Nanotechnology in the specific context of venture. So within this story, I should be talking about innovation at the center, but being a scientist and trying to avoid being too, business school-like, I will try to include some science in it. So hopefully some of you who did not know how Gecko managed to walk up walls, by the end of this talk you would know a little bit about it, and maybe some few other scientific facts. Okay, so the Nano Centre itself, as I mentioned before, was established 15 years ago. The very first thing that was done 15 years ago was to put money and resources, including human resources, into capital equipment, basically building a central facility. And it took many years, and within these 15 years we were able to build a very strong team supporting a very expansive and very extensive setup based somewhere between $15 to $20 million, depends how you count, of high-end, top-of-the-class equipment. In addition to this core activity, we have at the university, there are about 90 PIs, principal investigators, engaged in nanoscience and nanotechnology. Within this large group of laboratories, there are about 6 that are core laboratories, and they're all located in the same facility. Luckily, a few months ago, we launched a new project to build a new building for all that, so we will be able to expand it within the next few years and to host all this together in one place. There are hundreds of students. These are graduate students, not undergraduate students, graduate students, master and PhD level students. This is an extremely important point that I would like to mention when I talk about the risks towards the end. I'll try to remain very positive. It's completely against my nature, but I'll be relatively very positive for the most of the talk. But I will use the opportunity to talk about risks towards the end. So this is, for those of you, if there's anybody here who doesn't know what nanotechnology is about, this I think is a very good way of capturing the essence. In nanotechnology, a very good example, one of the prime example, is what you can do with carbon. So you all know diamonds. A diamond is one shape of carbon. And carbon can be produced artificially, as you know, using the right temperature and right pressure. If you use different conditions, you can end up with graphite. Graphite is one of the cheapest materials. This is what you have at the tip of your pencil, and it just peels off. So two systems made of exactly the same material, totally different properties. What started to emerge in the early 90s was a new class of materials built on carbon, so it's the same material, but instead of forming bulk material, they're nanomaterials. So the first one that was discovered was this C60, those buckyballs, which people didn't really believe that they could exist energetically, physically, chemically. Later on, there were the carbon nanotubes. These are, by the way, a couple of nanometers in size. So tiny, tiny things, little footballs, if you like, of carbon. So that was a big, big thing. And more recently, there's the graphene, which is a new material that everybody's talking about it, and everybody thinks that it's going to be the next electronics, next chemistry, next everything. Now, how was this facilitated? It was facilitated by very special microscopes. So for decades, scientists were working on improving the capacity to observe such materials. It was not a process where people thought, okay, we're going to find nanomaterials, so let's develop these special microscopes. The motivation was completely different. But somehow, at the early 90s, these things converged, and then people could finally see these structures. We could use technology that is now readily available, completely commercial. You can put these materials, fabricate them, and every undergraduate student can visualize them in no time. So really, when people started talking about nanotechnology, they talked about equipment at the very beginning. And this is what I mentioned before happened here at the university, a lot of investment into different equipment that could use many people for many different applications. So the core of the nano activity at the university here at Tel Aviv and in many other places was to build infrastructure so people can come and use and make new materials, characterize new equipment, measure new devices. And the users are from all across disciplines. So that's when the president before mentioned multidisciplinarity. This was a very big deviation from the standard model at the universities where you have the different faculties or the different departments. Here was an effort to say, let's focus not about the research or the motivation or the academic discipline, but let's use the facilities as something integral that people can use. And again, each one of these equipments could be hundreds of thousands and above $1 million a piece. Of course, the manpower that is required in order to operate these systems is very, very critical. And so when we talk about deep innovation and we talk about the real infrastructure that is needed for something like this, it's very, very important to remember all that. Now, as a side story to all this, it was very obvious, and people have been talking about it for many years, that nanotechnology is the big next thing, and there's an enormous amount of opportunities. And so when the government of Israel actually became a very major player in supporting the establishment of the infrastructure that I mentioned, it started at full strength in 2007, the idea was that there should be a lot of spill-offs of this activity. So, okay, you have basic research at the university, you have infrastructure, you have new ideas and new activities, but there should be a lot of commercial activity, and the Israeli, and this is a very important thing, the Israeli industry should gain from that. This is where you have to start establishing and thinking about the ecosystem. And so this is the map of what came out of Tel Aviv University Nano Centre from looking from 2007 until today. The point is that every logo here is a startup company, and every text, almost every text refers to a license agreement. So there are about 8 startup companies and 28, 30 license agreements. And now the question is whether this thing just happened, whether these things just happen, whether we should just let it happen, or whether there's something that should be done in order to promote it and make it more effective. So let me begin with a first example, and this is TraceSense. TraceSense, if you look at the map, started in 2009, 2010. Professor Fernando Potocki from the School of Chemistry, one of our core members, he basically developed the idea, well, it's not uniquely his, but a very special technology in order to build very, very sensitive chemical sensor. So I'll show you very briefly the movie. We may stop it at the...
TraceSense presents the world's first nano-based threat detection system. Identifying terror threats is an endless challenge. Security inspections become tighter, lines longer, and costs higher. Citizens' physical privacy is compromised. Threat detection must take place more frequently and in more locations. Terrorists constantly find new ways to overcome current security solutions, so existing measures become less and less effective. There is a need for effective tools that adapt to evolving security threats and enable non-intrusive, fast-track screening at lower costs. TraceSense has developed the world's first nano-based threat detection system, TESS. A small-scale portable device, TESS can detect a wide range of threats in gaseous streams and liquid samples at extremely low concentrations. TESS offers real-time, on-site detection of explosive, biological, or chemical hazards, also providing information on the specific nature of the threat. TraceSense's patented technology uses nano-ribbon pattern arrays on a small semiconductor chip, each element 10,000 times thinner than a human hair. Through proprietary chemical procedures, receptor molecules are attached to the nanoribbons, forming chemically specific nanosensors. When these sensors are exposed to the target substances, an instantaneous change in electrical response is triggered within the nanoarray.
Okay, so the point that I'm trying to make about the story of TraceSense is that TraceSense started from almost a textbook version of what you study in business school, and what my spouse tries to convince me every dinner, that innovation must have a problem. You start with a problem. So every night we argue because he said innovation starts with a problem, and I say, no, innovation doesn't necessarily have to start with a problem. And this is one of the things that I want to try to convince you, that often, and this is probably the biggest challenge that we face in academic setting, is that not always, or actually many times, we're finding ourselves in the opposite and very, very risky and very complicated world of trying to find problems after we have the solution. So sometimes researchers such as Fernando come in, they're very focused, they team up with an entrepreneur, and it still takes an enormous amount of time, enormous amount of money to take an idea and technology in order to bring it to the market. So TraceSense is just about to have their first products in the market. So 2007, 2010, and it's only now at the very beginning. Now, let me give you an example for what I mean. So this is an extremely well-known technology. I don't know if any one of you recognize it when you look at it through this picture. This is a technology that was invented in 1970 purely by chance. Anybody have a guess? If I tell you that it was developed at 3M, that makes it easier? The Post-it. So the Post-it was invented completely by accident, because the guy, Spencer Silver, who was in charge of developing a super adhesive glue, this was his task. He came up with a complete opposite. He came up with a very loose adhesive. And this is a very well-known story. It's not a myth, it's completely true. Now it's a $1 billion annual market. Again, a very, very famous story, very nice. The thing is, and I was very intrigued to see the full story, it wasn't just that the material was discovered by accident. It was the application, what to do with it, that took more than 10 years and was also by complete accident. And it was another guy, another friend, at 3M. It was not from the marketing, it was not the product development people, it was another scientist who basically had a need. He was singing in a chorus, in a church chorus, and he had the book, the papers with the notes, and he needed to keep the right page, and he didn't want, like some people that you don't like to fold the page, and he was using all sorts of things, and things were falling off, and they said, oh, this could be really, really, really good idea. So it took enormous amount of time, and the point is that within these 10 years, it's not that people were idle. Actually, the two investors, the main inventor, spent his own money to build a prototyping system at his house because he believed so much in the technology. So for 10 years, he was begging people at 3M to look into his innovation. Now, the point is, this is one story. So in principle, you could say, okay, there's nothing really to learn from that, but I think there's a lot to learn from this story. The point is that even if you have the best ideal conditions, and I think 3M is definitely a place where you could definitely say, okay, you have plentiful of resources, you don't have any legal barriers. The scientists were very eager, the scientists were running after the rest of the people in the company, begging for their attention. There was a lot of, the ecosystem was perfect, okay? Everything was perfect, and still it took so many chances and so many years in order to take something like that and turn it into a product. And so for the rest of the talk, I'm going to talk about this situation, that everything is ideal. I don't think the situation is ideal, but let's just assume for a second that everything is ideal. No legal barriers, nothing. Everything is just fantastic. The scientists are mature, everybody is just fantastic. But how do you match between the technology, which I say technology because it's not really a technology, it's just a poor adhesive material. It's not a technology. How do you take that and turn it into something that people would even pay attention? So that's the story. The story is you have something. This something, the scientist is madly in love with it, but how do you turn that into something that people that... Now, Gecko, so this is just a brief interrupt. The reason why this glue works the way it does is because of these bumps. And if you look carefully into the legs of Gecko, so this is an electronic microscope image of the foot of a gecko. And you zoom in and zoom in and zoom in and you zoom in, you realize that they have these little tiny hairs, nanometer in size, and this really what makes the geckos stick very effectively. And also the same thing with the paper, the way that you detach the paper is using the angle, so you gradually remove the adhesive material from the surface. So this was just a small mentioning of geckos because I want the title to be interesting. Okay, so let me give you some examples of the more common situation that we face, which is solutions looking for problems. So I'll give you the example of storedup. Storedup is another startup company that came out of the center only 2 years ago. And storedup, there's the...
This is a nanodup. It is 2 nanometers in size, shaped by the creation of nanocrystals or peptides, and produced with technology inspired by nature that turns science fiction into everyday science. We are storedup, and this bioorganic building block enables us to make groundbreaking innovations. From smart graphic displays, to flash memories, to image sensors, the nanodup lets us do things like no other material. And in the 30 seconds it took you to hear about it, it has already recharged your smartphone for the entire day. StoreDup's one-of-a-kind interdisciplinary staff includes experts from such diverse fields as biology, chemistry, physics, electronics, and engineering. Building on our unique integration of scientific talents, StoreDup has succeeded in harnessing the powerful potential of nanotechnology. Most importantly, we have used this green bioorganically sourced material to create a working smartphone battery that flash charges in 30 seconds and provides extended battery lifetime.
After intensive research,
Okay, I'll skip the movie. So this is in brief, since there are business people here, the history of storedup. This is from a site, I think it's self-reporting, so I don't know how extremely reliable it is, but the company is perfectly real, and I guess the numbers are pretty real. So June 2013, you can see the $6 million first investment, followed by a $10 million investment, followed by $42 million investment, and August 2015, another $18 million investment. It's, in my terms, in my definitions, this is a huge success. They have several tens of researchers. Many of them are own graduate students working in Herzliya, developing something that may work or may not work. I mean, nobody knows. But this is in a nutshell the business story behind this, and I'll say a few words about it. The important thing is that when a company starts before the $6 million, in the first round of even approaching the investors, the very critical part is the prototyping or proof of concept. And this is the point where the company needs to give answers very, very quickly. And this is the point where it was very instrumental for them to be nearby, actually working at the university, telling us, you know, the Samsung people are coming next week. We need to work, and we need your help and your engineers in order to help us deliver the needed prototype. So this is where, you know, a company working, or it's not even a company yet, it's something that is emerging, is working at the university, facilitating extremely expensive resources and working within, again, this ecosystem. So, but the story of storedup is really funny if you think about it. The story goes actually somewhere to 2003, maybe even before. And it started with researchers from biotechnology, Professor Udi Gazit, trying to understand the underlying principles of it's not folding, it's self-assembly of proteins into plaque structure in the brain of Alzheimer's disease patients. Okay? How do you go between that into rapidly charging batteries? Okay, that takes a lot of imagination, and that took nearly 12 years of going in all sorts of different directions, of different people coming in actually within, so it started with Udi, started with these ugly looking tubes that you see there. And the guy next to him, this is Professor Gill Rosenman from electrical engineering. And when Gill is looking at structures, organized structures, he doesn't think about Alzheimer's disease. He thinks about band gap structures. He thinks about electronic properties. He thinks about photonics. And they started exploring their photoluminescence properties. And they had some license agreement with that. So, and then he took somebody with completely different visions, and this is Simon Litzin, who's very, very oriented towards commercialization. And he looked at some of their papers and he said, okay, let's think about completely different things. And the final point in the story was basically an entrepreneur coming out completely from the outside and taking this technology and building the company. So this is the storedup company. Now, NanoAir is a totally different story. NanoAir is a story where we, as a center, we brought in this guy, the middle guy, Eran Fine, and we brought him as a consultant. And the point, and this is what Dan Wilensky asked us to do, he said, there are a lot of know-how at the university, and the challenge is how to take this and build new ideas through the understanding that it's not always obvious what we're going to do with it. And so Eran was looking and talking with people. It was a very lengthy process, very complicated process. Eventually he came up with a new idea, a joint idea with Slava Krylov, and they developed this new company that started just this year, NanoAir. And what NanoAir is developing is a paper-thin cooling device. And again, Eran was bringing in the motivation, he was bringing in the commercial thinking, he was bringing a totally non-technical thinking, but with the conversation with Slava, they were able to do something very special and very unique. Now what we're trying to do is this is another example of the same kind of thinking. So this is a work of Professor Shachar Richter. Shachar has been working with biomaterials, and in this sense, these are materials that are derived from biological materials. And in this particular case, it's a jellyfish. Now, it's a long story, but the point was that they discovered that if you synthesize the material from the jellyfish, you end up with a super absorbing material. And again, you're stuck with the same problem. Okay, so it's super absorber, it's cool, it absorbs blood like hell, but what do you do with that? And that was the beautiful story of taking that and trying to develop it into something mature, something that would make people interested. And it's always fascinating to show this process happening again and again. And when people mentioned before the ecosystem and the need to talk, yes, you need to talk, but you need to talk with people from the outside. You need to think completely outside the box. And I think that the lesson is that people within the system are not enough to generate. So what was the role of the center as a center in all this? So it really grew up. It really developed. So in TraceSense, we had almost no knowledge of what was going on. We basically provided lab services. I mean, it was like providing lab services to many other people. We didn't know, we're completely uninvolved. In storedup, we were already involved in the sense that we were providing help, as I mentioned, rapid prototyping, helping with the know-how and lab services. With NanoAir, we basically built the system. We paid a person from the outside to come in to look for something interesting. So this is the mentor. We provided a little bit of money for this process. So this is a nano seed funding. And we also help with the prototyping and, of course, the lab services. And with super absorbing material, again, the same thing. It's the mentor, it's the nano seed funding, the prototyping, etc. So the main lesson, and this is probably one of the messages that I want to deliver, is that mentor and solid proof of concept for these kind of studies, for these kind of technologies, again, technologies, because there's no technology, there's something new, but it's not really a technology. These are extremely important when we try to take all these things out. So I'll conclude with addressing the two questions about the opportunities and the risks. So again, trying to be positive, I listed a lot of opportunities, but I think the risks, as Yesha mentioned, are really big and really frightening, at least to me. So the opportunities is that if we do good job at delivering commercial innovation outside the university, we build new positions, and these new positions are needed because we're producing, well, I see that many of the academics are gone now, but we as academics produce enormous amount of graduate students. These graduate students, by no way that you can manipulate statistics, stay in academia. There's no way. And these people are highly trained, extremely highly trained PhD students. There are hundreds of them, and there are thousands of master's students, and if these students don't have positions, relevant positions, they're not going to stay here. They're going to go to other places where they have relevant positions. And I'm not talking about salaries, I'm talking about places where they can really use their expertise. And you, again, you have to understand that these are extremely highly trained people. Working with the industry, building these companies builds new collaboration. So I personally think that it strengthens the scientific research, even the basic ones. And I think what the universities must do.
Why is it a risk?
No, it's not a risk. It's still an opportunity.
Yeah. Why is there a risk to have too many dry students? Because they don't have a job.
Oh, because you're producing. Just stop the watch. Stop the clock. Why is it a risk? It's a huge risk because you're producing hundreds. Israel is producing hundreds of PhD students every year that do not have, in these fields, okay, do not have the relevant jobs in Israel to fit their skills. If you don't think it's a risk, then
You show a way to create jobs, right? With your companies. Yeah,
Sorry?
That's the solution.
that's the opportunity. That's the solution. Yeah. So now, what the opportunity for the universities, and I think this is what Yesha was saying very, very clearly, and I completely agree with that, is that it's all about responsibility. It's about also making clear what the university is interested in doing. And I think the taking responsibilities is really, really critical, and as we've shown, it makes an impact. If you make it your, in our case, we didn't have there was no choice, because we're supported by the government. The government, the INI, the Israeli National Nano Initiative, they told us, you have to do that, so we did that. I think that it's really about a commitment. It's really about defining the parameters of success. So we saw before a list of success parameters, and you can count the number of papers, you can count the number of patents, you can count anything you want. I would like to count the number of new jobs generated. Now you can say, okay, this is not our problem, fine, but then you're not part of making an impact. So this is really a very critical thing. And another thing is, of course, the role of different stakeholders. There are many, many stakeholders here. There's the industry, there's the government, within the university there are many different players, and I think this is very, very important. I don't want to talk right now about TTOs, but we can do that later. Let me just finish, and I'll be happy if Yesha allows me to answer questions. Now, the risks, one of which I mentioned, is the issue of producing too many students, which I think is a real problem. But the other thing, and it was mentioned by Yesha again, becoming irrelevant. So the university president mentioned that Tel Aviv University operates on $160 million a year of research budgets. But this is the direct research budget of the research authority that does not account for the rest of the government support that is provided, 1.5 million shekels that is provided to the university. And the reason why the university receives money from the government is not for teaching, because if it was just for teaching, we would not have this mega operation. So it's teaching and generating new know-how. So we have to justify ourselves all the time. Again, that does not mean that it changes our definition. It doesn't mean that we're not exclusively or primarily doing basic research. It just means, what do you do with the overflow of know-how that is being generated? Now, to conclude, as a teaser, I think that there were many reports all over the world, especially including in Israel, of what should be done, what are the challenges, what are the problems. But after many years of going through discussions and fights and arguing with people, I think the core, the really, really core here is really the underlying concept that the universities have to make a decision whether they are a true player in this or not. If they are, then there are the things that have to be, you have to define what are your mission statement, you have to define what your goals are, and then you can operate from there. But before that happens, I don't think that anything else, so I don't want to end with such a pessimistic, so let me just conclude that there's actually enormous amount of opportunities, as you saw before, and I think that it's very challenging to work in a field that is very long-term, very expensive, but on the other hand, very exciting and with lots and lots of great opportunities. So thank you very much.
This program was brought to you by Koller Institute of Venture at Tel Aviv University.